Hey guys, I'm going to give you a quick tutorial on understanding alpha, beta, and power. This presentation was actually created by a friend of mine who teaches over at Smyrna Park High School, Mr. Halmy. And I think he does a really good job of kind of laying out the relationship between alpha, beta, and power, which tend to be pretty confusing topics in AP Stat. And I'll be honest, sometimes it even gets me. So I'm going to start by just reviewing. I'm just starting off with an example. Suppose we're testing the hypothesis where our null hypothesis is stating that the proportion is equal to 0.3. We don't have any context or anything, so don't worry about it. But our null hypothesis is basically stating that the true parameter, the true population proportion is 30%, and the alternative is testing that we think that perhaps the proportion is actually greater than that. So if we think about the sampling distribution for p hat, we know that the center of this distribution is going to be at 30%. And we'll just assume that all of the conditions are met and that p hat is actually distributed normally. So we have a normal distribution with the center at 0.3. We don't know our sample size. We're not going to worry about that right now. So suppose we get a sample result and our p hat is really close to 0.3. Well, we know that if it's within a couple standard deviations of our mean, that's not that unusual. And so if we get a result that's not that unusual, that means our p-value is probably going to be pretty high. And that tells us that we're not going to reject the null hypothesis. Well, if we get a value for p hat, if we get a sample result that is very unusual, if it is very extreme, if it's beyond 2 standard deviations away from our mean, then we conclude it is unusual. Our p-value would be very low, and that would give us evidence to reject the null hypothesis. And so we would conclude that the alternative is true, that the true parameter is actually greater than 30%. And so sometimes we draw a line between the fail to reject and the reject. And we do that using our alpha level. So we can actually kind of work backwards. So for example, if we know that we're going to be using a significance level of 5%, we can work backwards and figure out the critical z value. We did this with confidence intervals. We can actually find the critical z value that would enable us to determine what we call a rejection region. So in this case, since we're doing an upper tail test, anything to the left of our critical z value would be the area where we would not reject our null hypothesis. But anything to the right of that would be what we would call the rejection region. So if we suppose then that the null hypothesis is true, we're either going to reject it or fail to reject it based on our evidence. So if p hat was really extreme, if it was beyond our critical value, if it's in our rejection region, we say it's unusual, our p-value will be low, and we'll reject our null hypothesis. But if the null hypothesis is actually true, that means that we're making a mistake by rejecting it. This is called a type 1 error. Okay, that's one of the mistakes that we can make. If the null hypothesis is true, but our evidence is so extreme that we ultimately reject it, that's called a type 1 error. Okay, and so the probability of making a type 1 error, we've named it, we have a special name for it, we call it alpha. It's the alpha level. And remember, the alpha level is the same as our significance level. We get to choose that alpha level in advance. If we want to be cautious, then we keep the alpha level very small. If we don't need to be as careful, then we can make the alpha level a little bit bigger. It really depends on the circumstances. If you're dealing with a situation where you're dealing with something that's going to cost a lot of money or something that's going to be hazardous to someone's health, then you want to be very careful and you want to have a low alpha value. But if you're just trying to, estimate the proportion of students that are going to prom, for example, or test a claim that really there aren't any consequences to making a wrong decision, then you can set your alpha level to be a little bit higher. It really depends on the consequences. So the first 2 big points are basically that our alpha level represents the probability of making a type 1 error. And the statistician then weighs the consequences of a type 1 error and then will choose the alpha level accordingly. Okay, so let's take another look at the situation. Now let's suppose, so here's our sampling distribution, and remember we're assuming that our null hypothesis, which said that the parameter was equal to 30%, if we assume that that's true, this is what our distribution would look like. Our normal distribution would be centered around 0.3. But suppose it's not true. Now we don't ever actually know this in advance, but let's just say that it's not true. So if we get a p hat value that is close to what we are assuming is true for our parameter, that means we're not going to reject it. It's not considered in our rejection region, and so therefore we're not going to reject the null hypothesis. It's not that unusual. We don't reject it. But if it turns out that the null hypothesis isn't true and we're not rejecting it, that means we're making a type 2 error. We're making a mistake. And again, we don't ever really know the truth about it. So the thing that's a little bit more tricky with a type 2 error is there are lots of alternatives that could actually be true, and we don't ever know which one is the truth. So if some alternative is true, then our distribution really isn't centered at 0.3, it's centered somewhere else. So depending on what the sample p hat would be that we're testing against, our distribution is going to change. So let's suppose then that the true proportion is at 0.5. That means that our normal curve is going to shift, and now the true mean is at 0.5. But notice where our p hat was, and notice the region that it's pointing to. This is called our type 2 error. This is called our beta. Sometimes we call it beta. Alpha refers to a type 1 error. Beta refers to the probability of making a type 2 error. It's really difficult to calculate beta. It's not something that you're tested on the AP exam. It's a little bit harder to determine the probability of a type 2 error unless you have a specific alternative in mind. And we're not going to go into the details of that. Okay, so we could never really know the true proportion unless we're testing against something specifically. So if the true proportion was actually 45%, notice that that changes the beta range. That whole area of making a type 2 error is a little bit bigger now. Okay, so we never really know the value of beta. We never know the probability of making a type 2 error. So the next two big ideas are basically that beta is what we call the probability of making a type 2 error. And we never really know how much beta is unless we're testing against a specific alternative, which we're not going to do. All right, so let's talk about power. Power is related to the probability of making a type 2 error. Power is basically the strength of your test to be able to detect a type 2 error, to be able to detect against an alternative. So if we get, so let's go back to our original example where we have our distribution centered around that null hypothesis of p equals 0.3. We have our rejection region. That vertical black dotted line corresponds to our critical z value. The area to the right then would be our rejection region. So if we get a p hat in that region, that means that it's unusual. Our p value will be low, and that'll tell us to reject the null hypothesis. And that's a good thing because if the null hypothesis is false, then we've made a correct decision. That's called the power of the test. It's basically the ability of the test to detect against a specific alternative. So if the null hypothesis is false, p hat wouldn't be centered there anymore. This is where it gets confusing. Our distribution would shift to a different center. And so that area to the right of our vertical line where our critical z value is, that is called the power of the test. The red region that you see is still the probability of a type 2 error. So you can see that the probability of a type 2 error, which is just beta, and the power of the test are complements of each other. Okay, so the red region is beta, that's the probability of our type 2 error. The power is the area to the right. It's that rejection region, but we've slid the distribution over where it should be centered around the true proportion, which we don't know. And so you can see if we adjust that alpha level, so that remember the vertical line corresponds to alpha. So if I start adjusting that, I can also affect the probability of making a type 2 error or beta, as well as the power. So power, because power and beta are just complements of each other, the power of a test is just 1 minus beta. So if the null is true, okay, and so again, we've got our rejection region, that's alpha. It's the probability of our type 1 error. And if the null is false, notice that we have our beta region, which would be when we fail to reject the null hypothesis when in fact it's false. And then we have the power on the other side of beta. So if I want to adjust my alpha level, because remember, we can set our alpha level. We set our level of significance, which also determines the probability of our type 1 error. And so remember, it depends on the consequences of making the wrong decision. So if I want to reduce the probability of a type 1 error, notice how it affects beta and power. The consequence is great. That means that the probability of making a type 2 error is going to be bigger and the power of my test is lower. And neither of those two things are good. So you might think, all right, well, so we'll increase the alpha level. So if we do that, now my alpha level is big. That's the probability of making a type 1 error. Now, it's good because I've reduced the probability of making a type 2 error, and I've also increased the power. So both of those things are good. But when I increase the probability of making a type 1 error, I still have large errors that I want to address. And so the question is there any way that we can reduce our errors and increase our power? And ultimately, yes. The big ideas, though, and you might want to jot this down because on AP drills and AP questions, you may not specifically be asked to calculate a probability of a type 1 or a type 2 error, but you will be asked ways in which you can reduce the probability of a type 1 error or type 2 error, or how to increase the power. So this little table that I'm going to show you might be something you want to jot down because it really does kind of summarize the relationships. We always want our alpha and beta, because remember, they're the probability of a type 1 and a type 2 error. We want them to be as small as possible. Okay, so alpha as small as possible, beta as small as possible, and we want our power to be as big as possible. Okay, so if alpha increases, remember that's our probability of a type 1 error, that's a bad thing. I don't want it to get bigger. But as alpha gets bigger, that is actually going to decrease my beta, which is the probability of a type 2 error, and that's actually a good thing. And if I decrease beta, that means I'm increasing the power, which is also a good thing. Conversely, if I decrease my alpha level, which would be the probability of a type 1 error, which is a good thing, the consequence is going to be that it's going to increase the probability of a type 2 error and decrease my power, which are bad things. So it's important that you understand this relationship because the AP questions that you're going to be given are probably going to be centered around these relationships. So the question is there any way that we can decrease both of the errors at the same time? The answer is yes. If you think about your two distributions, so the one on the top is where we assume that the null hypothesis is true, and so it's centered around the null hypothesis. The second graph you see is where some other alternative is true, and so the graph of our sampling distribution is actually centered elsewhere. And so if I want to decrease both errors, notice that if I can somehow shrink my graphs, that it will shrink both errors and increase the power at the same time. The way that we can do that is to reduce the standard deviation. And the way we reduce the standard deviation for our sampling distribution is simply increasing the sample size. So increasing your sample size is generally the best thing you can do when you're dealing with inference. You just got to make sure that when you're taking your sample that there's no bias. So you want to make sure that it's a simple random sample and you're using really good sampling techniques. So the last big point basically is this. The only way to decrease both alpha and beta and increase the power, because remember, power is good, alpha and beta are bad because they represent the probabilities of our type 1 and type 2 errors. The only way to do this is to reduce your standard deviation by increasing the sample size. So I hope this sort of summarized everything in a way that makes a little bit more sense. And I do want to just, again, thank Mr. Helmy from Severna Park. I hope this helps.